All right, final part is about titrations. Now, this is something you've never heard of, you've never seen, but I want to take the time to at least show it to you. So if you do have a question, and I just have a gut feeling you're going to see this year on this exam, I don't know why, I just do, but I don't want it to be like a foreign language. I want you to be able to pick out the high points and see if you can at least scratch a point or two out of it. So it says laboratory procedure used to determine the concentration of a solution. So let's start there. It's a lab procedure used to determine the concentration of a solution or the molar mass of an unknown substance by reacting an unknown with a known. I don't know when you're like, what are you talking about? So basically what we do is we take the concentration of a known acid or a base and we drop it in an unknown concentration. And from certain parts of the drops and the concentrations and the volumes, we can determine what the concentration of the unknown is. It can only be used if the stoichiometric endpoint. Now, you have a good way for them to remember the endpoint? Perfect. And again, that's kind of the hardest part about them understanding the difference between, because the endpoint and the equivalence point on the graph are the same, but the words mean something different. So the endpoint, use your eyes. Your eyeballs will tell you when the endpoint occurs. And the way you will know is because a color change occurs. That's with the lab procedure. Now you can use a pH graph and all with the equipment and stuff like that, and it'll show you. But that's the big indicators of color change. So the endpoint, it can only be used if the stoichiometric endpoint can be monitored. Plotting the pH of the solution can be analyzed as a function of the amount of titrant. And we're going to talk about what titrant is in just a second. The equivalence point, put a big star beside that. Okay. The equivalence point is when the titration is when enough titrant has been added to react, and this is the key word right here, exactly with the substance in the solution. So there's two words here that are weird. Titration, titrant, and titrated. Yeah, I can count to 3. Okay. Titration is the process. Titrant is the drip. And this will make sense in a minute. It's what's being added. The titrant is what's being dripped. And the titrant is, what's being titrated. Yep, it's the beaker. Yeah, solution will work. The endpoint of color, the endpoint is a point of color change with an indicator. Now there's several different indicators. Brothomol blue, phenolphthalein, phenol red. Those are the 3 common ones. Like I said, I know all this is foreign, but I see it. All right, so acid-base reactions to titrations, nothing important there. So basically, they took this acid. Everybody know what acid this is by name? Oxalic acid. And they mixed it with what? Strong base. And they're going to try to determine what one of these concentrations is if we don't know them. Okay? So this is what a titration is. Does anybody know what the name of that big long tube is? It's called a burette. It's right down here in the very bottom. It's called a burette. It's a big, huge, long tube. Most of their time, I think they're like 100 milliliters. Is that right, Ms. Sullivan? I think most of them are 50 or 100. Okay. Yes. Okay. This little blue thingy he has in his hand, I'm not even going to tell you the name because all you'll do is giggle. How about I write it? Okay?
Are you for real?
Dead serious.
Why would you write that on the board, Richard?
In the recording.
It's a chemical thing that it's real.
Parents gonna come
That.
What is he taking you?
This and my other favorite one of all is the rubber policeman. I think those are the two funniest ones. It's a little rubber tip that goes on a glass rod that you use for stirring. It's called a rubber policeman. Okay, all right.
You were wrong.
This is why I don't like to tell y'all things. All right, so this right here is going to be the known. Correct me if I'm wrong. That's the titrant, correct? Okay. All right, so again, the known, can't see that. Let me pick a better color. This is the titrant in the top. In the beaker, way down here, is the unknown. And so what we're going to do is we're going to go drippy, drippy, drippy of the titrant into the unknown. So what do I mean by known? And I guess let's go back and add that because I should have done it at the beginning. It's a known concentration. So just put brackets around the word known. So we know the concentration. So notice down here in the very last part, let's just read the words. A, 50 milliliter burette containing aqueous NaOH of an accurately known concentration. So like I said, in this burette, there is a known concentration of sodium hydroxide. B, a solution of NaOH is added slowly to the sample being analyzed, and the sample is mixed. Now, the way you would mix this is obviously either stir it, or they actually have these things called a magnetic stir rod. You drop the little magnetic stir rod in, you turn it on, and it spins it for you. Okay? And C, when the amount of NaOH added from the burette exactly equals. So let me zoom in on this part right here. When the amount of NaOH added from the burette exactly equals the amount of H plus supplied, there is a color change. So now, in this solution, this is our WA. And what is WA? Do you agree that this weak acid has a specific H plus concentration? What are we dripping into this thing? We're dripping OH minus in that solution. So what we're trying to figure out is every one OH minus we drop, we've got one H plus adding together. And what do OH minus plus H plus add together to give you? Water. So what we're trying to find is when we've neutralized and we've equaled out all of those H pluses. Because if I know the H plus concentration, can I know the concentration of the acid? Yes, that's why they do this. Okay? So from here, titrations. Added solution to the burette. This should be the known. And again, out here, do y'all have this? This is the titrant. The titrant released and reacts with the solution in the flask. This is your unknown. Do you have to have a base in the burette? No, it can be an acid. You may not know the base. You can do them vice versa. The indicator, which should also be in the Erlenmeyer flask, shows when the exact stoichiometric reaction has occurred. This right here is the most important thing right here. The moles of the acid equals the moles of the base. Out beside this, I want you to write this word. This is the equivalence. Thank you. The equivalence point. The equivalence point, obviously equal, but what is equal? When it says moles of acid, so the H plus must be equal to the OH minus. But here's the problem. Does the solution have to be neutral? No. The solution does not have to be neutral. That's the important thing. Okay? This is called neutralization. Now, so we have this right here. And so notice what we have. Down here in the flask, we have a flask containing a vinegar and indicator. The burette containing a base. Now, we've always talked about this. How do you measure something in a graduated cylinder from the bottom of the meniscus? This is very important. 39 and 40, so we're going down. So 39.1, 0.2, and then it's between 39.3 and 0.4, and so it's a little above. And so like I said, move your eye to the level of the liquid surface. So this is just kind of another picture of how you would read this. All right, so titration, a pH meter or indicator. We're going to use indicators. pH meters are a little bit more difficult to use to determine when the solution have an equivalence point. And I'm going to ask this again. What does equivalence point mean? Whenever the H plus equals the OH minus. Does it have to be neutral? No. So when the acid of that equals the base. Titrations are stoichiometry problems and nothing more. Treat them that way. If you're not using a balanced chemical equation, and if you don't include a mole-to-mole conversion in your calculation, you're not doing things correctly. Even if the mole-to-mole conversion is mathematically trivial because the relationship is 1-to-1, include that into your work, and I'll show you what I mean in a second. So before the titration lab can be done, these are some things that must be. So here's why I'm sharing this with you. Let's pretend that you get a question. We want to run a titration. Set the lab up for me. These are some things you would have to include in that explanation of this is how you would do the lab. The first thing you'd have to do is you would have to take the burette and you would have to rinse it 3 times. Now, why do we want to rinse something 3 times before we ever begin? Make sure any water is out of it. Make sure any dust is out of it. And what we're actually having in that burette is pure solution. Exactly what we want. Notice what else it says. Not only does it say the burette, it also says what? And the tip. Because if we wash it out with water, if we have a little bit of water on the end of the tip and it falls in the solution, could that knock off a concentration? And guys, let me tell you, when I say this is very, very delicate, one drop can throw the entire thing off. So water, it is very, very particular. Okay? This will remove any leftover water which can neutralize the titrant. A solution must be standardized, and we're going to talk about what standardized means in a second. To standardize a solution means to determine its actual concentration. If you walked in a chemical storage closet and on the bottle it said 0.5 molar NaOH, do you think that bottle is exactly 0.5?
Probably some of it's been used.
Some of it either has been used, it may have evaporated, something may have happened to it. So standardization is making its perfect concentration. So you can't say 0.5 just because the bottle says it. Okay? When an acid or base solution is prepared from commercially available starting materials, what is commercially available?
Like in a lab.
Like if I go buy some from a store. Okay? Can I go to Walmart right now and buy vinegar?
Yeah.
Will it have the molarity on there? I don't know if it does or not, but I need to figure it out. Okay? We are fairly confident in its concentration to 1 or 2 sig figs, but we need to be more certain of its concentration. We usually need to titrate it to determine its actual concentration. So that's called the standard procedure. So this is why we need to standardize. NaOH is an inexpensive, highly soluble, relatively easy to use base. It's often the go-to chemical for simple titrations. However, it's far from perfect. First of all, solid NaOH pellets absorb water. So if you're starting with solid NaOH and you dissolve it to form your base, could it have potentially absorbed a little bit of water before you created your acid? So what's that going to do to your calculated concentration? It's going to make it a little less than, the actual is a little less than calculated because of the water that was present. That's basically hydrating the solid. So accurately weighing a sample during the preparation of a solution is impossible because even while it's sitting on that weigh boat, it's absorbing the moisture from the air. Secondly, a solution of NaOH tends to absorb atmospheric carbon dioxide, which is weakly acidic. When you take something that's acidic and something that's basic, what happens when you mix them? It's that N word. They neutralize. This reaction between CO2 and NOH partially neutralizes the NOH solution, which means that a 0.1 molar solution of NaOH you think you're preparing today will not be 0.1 tomorrow or within the next hour. So if I did a lab in second period and it was 0.1, what are the chances of it still being 0.1 in sixth period? 0%. So it's going to change. For this reason, it is necessary to standardize NaOH solution to be used in titrations, even if you're extra careful in your measurements while making these solutions. So, going back, the first thing you got to do, rinse the burette and tip 3 times. Second thing, standardize your solution. How to standardize? I don't think I want to waste time. Sources of error, you read through that. 5 things to be able to determine about a titration curve. Did you kind of hit these? I think this is the most important thing. This is why I want to show you this. First of all, the starting and ending pH. The starting and ending. Oh, okay. This makes sense now. The starting and ending pH and the pH at any point, the equivalence point, the volume at the equivalence point, the pH at the equivalence point, and determine if Ka or Kb is either solution is either weak or acidic. Weak or strong. Did you talk about the half equivalence point with the weak and all that kind of stuff? See, I don't know if I have time to really cover all of this.
If you can, if they can watch at some point Renee's video and then give them the free response, there's a wonderful free response dealing with a titration curve. And it hits every single point in that video.
Oh, wow.
It was really good.
Okay.
Do you know what pKa is?
Just the negative log of the Ka. It's the half equivalence point. So you find your equivalence point, volume, half it, and then wherever it falls on the curve is your pKa. Yes. Okay. All right, how to read a titration curve. You should be told what your starting solutions are. If not, look on the curve where the curve starts. The top of the top of bottom of what? I don't know what that's supposed to say. It may supposed to be or. The top or bottom of pH is the y-axis in comparison to the volume on the x-axis. All right, so this will make sense. If you're looking at the pH, which is the y-axis, if the pH starts below 2, it's strong. If the pH starts above 2, it's weak. If it starts above 12, it's a strong base. If it starts above or below, if it's 7 to 12, it's weak. Let's just actually look at one. Here we go. All right, so let's down here and look. First of all, notice your axes. What is the y-axis? The pH. What is the x-axis? Very good. That's what we're looking at. So let's actually, very good word, Seth. Write the word titrant down here. Have you done this before? You just used the word I wasn't expecting. Okay. Now, so when we're starting down here at the initial point at xy intercept, what is the pH of this solution? What's the pH? 1. So what are we starting with? Strong acid or weak acid? We're starting with a strong acid. So this is what happens. We go drip, 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 drip. What are we dripping into this solution? Strong base, right? So notice what happens. Notice there's a change in pH, and then all of a sudden we reach this point. What does the equivalence point stand for? H plus equals OH minus, right? So if we continue to drip, 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 drip more strong base, where does the pH end?
13.
Way up here, right? So strong acid or weak, strong base or weak base? Strong base. So this is a curve of a strong. Do you see how that is? Based on where it starts and where it ends? Alex, are you with me at all? I didn't think you were. Huh? Say that one more time. Is the equivalence point at the pH of a 7? Yes. Why? Who won in a strong, strong battle? No one. So that means the solution will be neutral when? At the equivalence point.
It doesn't have to be, right?
Doesn't have to be. When would it not be at 7?
It's like a strong base and a weak acid.
Perfect. And that's what we're getting to. But let's look at the opposite effect. This time we're adding acid. But what did we start with at 0 drops? So you know you're starting with a strong base, Alex. You really want to kind of pay attention to this. Okay? So we drip, drip, drip. What do we know about HCl? It's a strong acid. Well, eventually we're going to add so much of this stuff. Look way down here at 50 milliliters. What has turned into the pH? It's turned into strong acid, right? But what do we notice about the equivalence point? So we did strong strong acid with a strong base. Did you do that too?
I did something very similar with the word acid.
All right. So notice again, the equivalence point is 7 because strong, strong. Nobody won. So let's look at this one is a little different. Or is it? Where did you start at the pH? Starts at 0. So what is that? That's a really strong acid. When we look up here at excess base, where are we? What pH? 13. So what is that? That's a strong base. We have no idea what either of these things were, but we know based on where their pHs began and ended, what we used. What is the equivalence point in a strong, strong? 7. So our pH is going to be 7. So the moles of H plus are equal to the moles of OH minus. Does that make sense?
Makes sense.
All right, good. This is another one I really like this picture because I think this is the one Jamie Benigna put out from the summer, and I really like some of this stuff. So if you notice down here, we start with a pH of 1. So what does that tell us about the acid? It is a strong acid. And so we're going to go drip, 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 drip. And if you look at the pictures, the initial acid concentration, why are there a bunch of ions in that initial concentration?
Because you haven't dripped them, right?
No. What do we know about strong acids? 100% dissociation. Notice what we have in the next picture. We have a little bit of NaCl dropped in. Excuse me. We have a little bit of, whoa. Yeah, we dropped NaOH. We've had the sodium ion floating around, right? And so this is the next picture. And then right here, what has occurred? Why do you know the equivalence point has occurred? Because there are no H pluses and no what? OH minuses. They've all neutralized themselves, right? So at this point, we've got H plus equal to OH minus. That's what's going on at this point. According to the curve, where is the pH? At 7. But with our eyeballs, notice those two lines. Can we see if that change occurred with our eyes? Why can't we?
Because it's too small.
Alex, you were looking at your phone. You have no clue.
What's a logical answer?
All right. Now, so this is what you don't understand. What are these two color things? Indication points, which are caused by indicators. What is the indicator for the top one? That purple changey thing. Phenolphthalein. What is the orangey changey thing?
Methyl red.
I said those two earlier, right? I said phenolphthalein, methyl red, bromolyl blue. Those are the three major ones. Could we use phenolphthalein or methyl red to do a strong, strong titration?
Yes.
No. The color change would not occur at the equivalence point. That's a problem. One that would change when? We want it to change right here, which methyl blue does. It changes from yellow to blue. They only change within that area, within that region. If they're outside of that region, you can't see it change. Sir, you have to know what you're dealing with. And we're going to talk about that. But let's look at the final. Guys, right here, the very last picture, notice where this box is drawn. It is drawn in this area of the curve. What do you notice in that very last box that's showing up that hasn't been present? Why is a bunch of OH starting to show up? Okay, but what is no longer there to absorb that OH minus? There are no more H pluses to absorb that hydroxide. So now do you see why the pH continues to become more and more and more basic? Because what are we adding more and more of? More and more and more and more OH minus. Now, why does it not... Now, I'm going to try to zoom in to show you this. Why does the pH not just continue and continue and continue and continue to rise?
Because you're at the pH of that base.
Exactly. That base that we're dripping has a certain pH. And it can't exceed that regardless of how much we put in. That's the exact reason why. We're only going to be able to add as much OH minuses as the solution has present in it. So we basically exhausted all the OH minuses. Okay, it's a perfect answer. Oh, real quick. Okay, now let's look at this one. Is this the same picture?
Yeah.
Please tell me I didn't just erase all that. I think I sure did.
It's a back button.
Oh, I know what happened. They're basically going through the curve with you. Just before and after the equivalence point, the pH is increased steadily. At the equivalence point, the moles of acid and the moles of base are equal, and the solution contains only water and the salt because everything has neutralized. So that's kind of important there. A base, as more base is added, increase in pH again levels off. So that takes you through each part of this. All right. So this is the part what I want to show you of how can we tell that we're dealing with weak versus strong. Do you notice that where we started with both of these lines has a different pH level? How can you tell that the blue line is a weak acid based on its y-axis? Based on the y-axis, it is above 2. So this right here tells me it's a weak acid. Did you also talk about the bump, the hill? Okay. You can barely tell on this one because this one is a bad picture. But anytime there's a weak acid, matter of fact, let me go to this picture. This is a good one. Look for the small rise in the beginning, meaning it's a weak acid. So there's two indicators. Number one, it's above 2. And number 2, look for this little hill. Here's what I want you to understand. If Mike Tyson and Evander Holyfield got out there in the ring, do you agree that they're pretty equivalent in strength? And they slugged each other in the face.
They'd both be knocked out at the same time.
Okay, good point. But here's the point of emphasis. Can someone strong take the hit of someone else that's strong and be affected very little and be effective?
Yes.
Not drastically. But what if Mike Tyson punched me in the stomach? Would I be drastically affected instantly? Yes. So here's what I'm trying to get you to understand. I've got a weak base sitting in this solution, and then I'm fixing to hit it with a strong base. Is that strong base going to punch the wind out of it? Sure. Yes. This is why that there's this instantaneous drastic change in pH. It's because you've got a weak thing, and all of a sudden that strong base punches it right in the gut. And there's a big change because it's been affected. Now, once they start swinging and punching, what does that weak base kind of do? It settles down, it realizes what it's up against, and it slowly kind of levels itself back off. So do you see why there is a drastic change at the very beginning? So when we kind of back out on this, again, the whole concept of this is that you can recognize that it's weak by two things. One, the pH is above 2, and 2, that little hill. But here's the point that I kept asking. Does the equivalence point have to be neutral? No. When did the equivalence point occur? And first off, I guess I left this out. How do you know it's an equivalence point based on the graph? Do you agree that right here and right here is when it kind of becomes vertical? It is the midpoint of the vertice, of the vertical line. So what is the pH of the midpoint of the vertical line? 9. Why would you have a pH of 9 in this particular titration? It's a strong base versus a weak acid. It's easy. You just got to hear it and see it to figure it out. But what if I were to flip this and give you... Oh, man, this is not what I wanted. I started an hour late. I'm not going an hour long. I just want a few more minutes. Okay? But what if I were to flip this and give you a strong acid and a weak base? The pH would start towards the top, right? But less than 12. It'd have a quick spike. It'd level out. But where would the equivalence point be? On the acidic side or the basic side? The acidic side. So real quick, let's just run through these. We've got a weak acid. First of all, what acid is that? Does anybody know? Very good. This is vinegar, acetic acid. Okay? So we're adding strong base, sodium hydroxide. At this point, we have the equivalence point. There, our H plus is equal to OH minus. That's all we have. And then finally, we're just dumping a whole lot of base in it, and we're going to get some hydroxide left. So again, how can you tell based on this curve that it's a weak acid and a strong base? You're a little bit above 2, and you've got the hump, and the pH at the end is above 12, right? Now, could I see this with my eyeballs? How can you? The equivalence point changes in the phenolphthalein area. What would it change from and to? It would go from colorless to pink. And that's what phenolphthalein does, okay? No, it goes from yellow to orange. This graph just doesn't have the bromomethyl blue on there. I don't know why. Okay? So here's something, last little part. Titration of a weak acid with a strong base. With the weaker acids, the initial pH is higher, and the pH changes near the equivalence point are more subtle. So basically notice, the Ka, the larger the exponent, the weaker it is, right? So this is really weak and this is really strong. Notice how big of a change happens when that weak acid gets punched in the gut by that strong base. Does that make sense? The weaker the acid, the more it's affected. Do y'all see how that works, kind of? Or am I crazy? Okay, I am. That's better. Okay. Last one. Strong acid with a weak base. How can you tell we started with a weak base? The pH is below 12, and what else do you see? You see that little punch in the gut, right? That strong acid kind of just dropped it just a little bit. How do you know it ended with a strong acid? Good. The pH is below 2. And then where is the equivalence point? It's at 5. Why not 7? Strong acid versus a weak base. The last. All right, so could I see this one with my eyes? Why? The equivalence point occurs within a color change region of which indicator? Methyl red. And then the last one. But notice top right, the AP exam will never contain this type of graph. What type of graph is this? Weak, weak. Now, honestly, I kind of discount this graph a little bit. I don't think you'd get that big of a little change. But you might. I think it's a little more subtle. But where is the equivalence point and why? Why 7? Nobody wins. Weak, weak. Still, it'd be watching like two pigeons fight, but okay. But you kind of get the point. And then the last thing is that Ka is equal to Kb. And last thing, I promise I'll let you go. I promise I'll let you go. What type? Let's answer these questions. Type of acid, type of base. Weak acid, strong base. The pH at the equivalence point. 9. The volume at the equivalence point. 10. 10 milliliters. And then the Ka. This is the part that I want to talk about. We're going to end the lecture. The pH is equal to the pKa at the half equiv point. So this is going to make sense. What is the equivalence point? 9. What is the volume at the equivalence point? 10. What is the half volume at the equivalence point? 5. What is the P? So at this point, what is the pH? 4.75. Are you with me? So what is the pKa? They're equal. You with me? The pH is equal to the pKa at this half equivalence point. But what was the question? Well, that's interesting. If I know the pKa is equal to 4.75, how do I get the Ka is the inverse of the negative 4.75, which would give me something. Do you see the difference there? Yes. So again, this is a diprotic. The reason you know it's diprotic because it has 2 humps. Trying to get to a different one. Triprotic has 3 humps. All right, last point, last one. So if I wanted to know, just please stay with me. What if I want to know the K? Because I want to make sure that you get this half equivalence point thing. The Ka is equal to the pH to the pKa at the half equiv point. What is the volume at the equivalence point? 1. So what's the half point? 0.5. The pH is equal to that, right? So we would take the inverse log of that number. You with me? That's it. We're done. Y'all have a good day.